everybody. In this episode, we are going to study few more aspects of interference. In the previous video, I have discussed that when two waves of amplitudes A1 and A2 having a constant phase difference delta between them interfere, the intensity of the resultant wave is obtained as I equal to A1 square plus A2 square plus 2A1 A2 cos delta. If A1 is equal to A2, that is the two amplitudes are equal, then the maximum intensity is obtained as 4A square when delta is equal to 2m pi, and minimum intensity is obtained as 0 when delta is 2m plus 1 pi. The interference pattern as observed with using this information is obtained as shown here, that is at 0 the intensity is, this is x axis we are plotting delta and y axis we are plotting intensity. At delta equal to 0, that is this, we are getting the maximum intensity which is 4a square. Then at pi, which is odd multiple of this that is minimum intensity, we are getting the intensity as 0, and so on. That is at 2 pi we are again getting the maximum intensity, 3 pi we are getting the intensity as 0, and again in the negative direction of x axis we are getting similar kinds of data. Plotting them we get this kind of curve. So from this curve it is apparent that there is some loss of energy or loss of intensity. Now we will see that whether this is actually true. To find out, we will first find out the average intensity in the range 0 to 2 pi. To 2 pi, we will integrate this . Integrating this from 0 to 2 pi, we will directly get 1 by 2 pi this, and cos delta integration is sin delta. This is, if we put this 0 here, we will get 0. So we are getting A1 square plus A2 square 2 pi. Now see, if we put here sin delta, if we put 2 pi, we will get 0, and again with 0 also we will get 0. So this will get nothing but 0. So what is the result? We get A1 square plus A2 square. This is the average intensity between the interval 0 to 2 pi. Again, the intensity when the two waves do not interfere, then also the intensity is what? Intensity is just the sum of the square of the amplitudes of the individual wave when the two waves does not interfere, which is, see, these two are equal. So we can say that there is actually no loss of energy, there is the energy is conserved, only there is a redistribution of energy, that is energy from the dark points, these are the dark points, is shifted to the energy, shifted to the bright points. So there is actually redistribution of energy. Now we will study the fringe width. First, let me tell what is fringe width. Fringe width is actually the distance between two consecutive dark or bright points. Now, suppose this is a source again as before. This source we are getting by putting this light from here to here, we are getting this two virtual coherent sources. Suppose P is a point on the screen, this is the screen. P is a point on the screen. The distance between the virtual sources and the screen is d, and between this distance, that is the distance between the two sources, is small d. O is the origin. Now we will find out the path difference. So, S to P, this distance will be equal to what? By Pythagoras theorem, it will be d square plus, suppose here to here this distance is x, then this distance will be d by 2. So, x plus d by 2 square, and S1P will be equal to, this is d, so this is again d by 2. So, this will be equal to d square plus x minus d by 2 square. The path difference between these two waves will be S2P minus S1P. Square. S2P minus S1P. Now S2P and S1P, this distance if assumed to be very near to the origin, that is x is very small, then this will be approximately equal to 2d. So this is equal to 2d S2P minus S1P. This is the path difference. So S2P minus S1P will be equal to this by 2d. Here if we put these values, we will get d square plus this square and this square cancels, we get x square plus d square by 4 plus xt minus x square minus d square by 4 minus plus xt. This one cancels, we get 2xd by d, 2 cancels, we get x d by capital D. So this is the path difference. Thus we get the path difference delta is equal to x d by capital D. Now we know the path difference for bright fringe is m 2m lambda by 2. Therefore here x d by capital D equal to m lambda and x equal to thus m lambda capital D by small d. So this point P will be bright point if this condition is satisfied, that is x equal to m lambda capital D by small d. Now for this point to be a dark point, this is for bright point. For dark point, the path difference should be equal to 2m plus 1 lambda by 2 or x by capital D should be equal to or x should be equal to 2m plus 1 lambda d by 2 small d. So this is the position of dark point and this is the position for bright point. So what we are getting? We are getting alternate points which are dark and bright. Fringe width is obtained by the distance between two consecutive dark or consecutive bright band. That is represented by beta. So beta will be for bright points will be m plus 1 lambda d by small d minus m lambda d by small d. This is equal to lambda d by small d. Again for dark points, beta equal to, this is for bright, for dark, beta equal to 2m plus 1 plus 1 lambda d by 2d minus this. From here we will get 2m lambda d by 2d. This one will cancel with this. We will get lambda d by 2 cancels, d plus this one and this one cancels. So we get again the fringe width for dark bands also lambda d by capital D. Thus we get the fringe width for both bright and dark bands are equal and they are equal to lambda d by small d. Fringe width lambda d by small d. From here we can tell the fringe width is independent of M. Then if we increase the wavelength, that is if we decrease the frequency, then we will get what? Fringe width will increase as B is directly proportional to the wavelength. So if lambda is increased, then the fringe width will increase, provided D, capital D, that is the distance between these two, and small d remains constant. And if lambda is decreased, the fringe width will decrease. So these are the points that we should remember, that is for beta it is independent of M, fringe width for both dark and bright bands are equal, and it is directly proportional to lambda. So if we change lambda, accordingly beta will change. Now we will study the shape of the fringes. For this we will consider the same kinds of drawing, that is, this is the source of light, monochromatic source of light. Screen is placed here. A point on the screen is designated as yx. Y is in this direction and x is in this direction. This is considered the origin of the coordinate system. This is the slit 1. Its position is 0 d by 2, and this is the slit 2. The distance between the two slits being d. This distance is y. Two waves from here, and again superposing and reducing interference pattern. Again we will find out the path difference. Here path difference is equal to S2p minus S1p. This gives delta plus S1p is equal to S2p. Is equal to, what is S1p? S1p will be equal to root over of y square plus x minus d by 2 square. By squaring and like little bit of rearrangement, we can obtain again squaring both sides and rearranging the terms, we can get this equation x square by equal to 1. These are the equations of hyperbola. So the fringes produced, what is this point? This is the point, a particular point. It may be bright or dark. So the equation, suppose this is a bright point, so that equations which represents all bright point is represented by the hyperbola. So if we plot this, we will get these kinds of curves. Thus we see that the loci of points of constant phase differences represents hyperbolae with S1 and S2 as foci on the x-axis. If we put the screen on like this, which is parallel to the slits S1, S2, we will get alternate bright and dark points like straight line. But if we put the screen like this, which is perpendicular to the S1 and S2 slits positions, then we will get concentric bright and dark circles. Fringes with white light. Now the position of bright fringe is where x is the position. Suppose this is the center region, this distance is x, as we have shown in the previous diagrams. This is the center bright band and x is this distance. Suppose P is the bright point, then we get its position as this. Now if M equal to 0, we will get the central bright band, that is this position. If we use white light, which is a combination of all the wavelengths, so at M equal to 0, we get x equal to 0, that is the central position. So in the central position, all the wavelengths will coincide. So the central fringe for the white light will be white in color. That is, all the wavelengths will come and it will reach this point, and so it will appear white in color. But what about the other bright fringes? Suppose M equal to 1, then we get x equal to this. We know lambda r for wavelength for red light is greater than the wavelength for violet light. So x r will be greater than x of v. That is, for red light, the position of bright point will be more away than for this violet light. So the fringes other than the central fringe will appear colored with the red in the outermost points and violet in the innermost region. In this way, we will get various colored fringes. Now, this condition, that is obtaining various colored fringes using white light, this one is valid only for small values of m. Small m. If m is large, then the path difference which is this for bright points, if m is large, we get the path difference is also large. So in that condition, the point, suppose a particular point, that particular point, both the conditions for constructive and destructive interference may satisfy at a particular time, and thus we will get uniform illumination rather than getting any particular color. Conditions for sustained interference. For sustained interference, the two sources must be coherent. That is, they must emit light waves having almost same amplitude, same frequency and having a constant phase difference. Then the interfering waves must have the same state of polarization. The polarization state of the two interfering waves must be same. Now, conditions for good observation. For observing the fringes properly, that is, we know x is equal to m lambda capital D by small d. This x, to observe each fringe properly, this x must be greater. So d should be greater, that is the distance between the screen and the slits, and the position of the two slits, that is the distance between the two slits, should be small. So this will make x larger. So this gives the condition, the separation d should be small, capital D should be large, and the background should be dark. So these are the conditions of good observation of fringes. And conditions for good contrast. For good contrast, conditions for observing good contrast fringes, amplitudes of the two waves must be equal. The sources must be monochromatic. And the sources must be narrow. The sources must be narrow. If the sources are not narrow, then what we will get? We will get a uniform illumination. Why? Because each point will produce an interference pattern. The interference pattern of all the points will overlap, and the result will be, we will get a uniform illumination on the screen. So we will not get good contrast fringes. So these are the conditions to obtain fringes with good contrast.